Hey everyone, welcome back. In this video, we are going to continue our discussion of pipelining. Specifically, we are going to be talking about the general considerations of pipelining and the advantages it offers. Specifically, we are going to be looking into speed up ratio, and throughput. And then we are going to take a look at some relevant exercises. We will solve some numericals related to these concepts. So let's begin. First, with a, a statement of the primary advantage of pipelining, right? So pipelining finds much utility in applications that need to repeat the same task many times with different sets of data. And this is something we discussed in the previous video as well. If you have some kind of application where you have to perform the same task but with different kinds of data values, we try to perform it using pipeline because we set up a circuit in advance depending on what kind of operation we are supposed to perform, and then we keep feeding it different values, keep feeding the pipeline different values, and it will perform the same operations for which it has been designed, and it will give us the results in a very efficient manner, more efficient than what would have been possible using a non-pipeline system. But again, like we discussed in the previous video, this is an advantage, but on the con side of this is the fact that pipelines require a lot of resources to set up. So unless you have an application where you need to perform the same task repeatedly, we should avoid using pipelines, because setting up a pipeline takes a lot of effort, time, and energy, and it's only cost effective if you're going to use it many different times. Otherwise, a non-pipeline system works much more efficiently. All right, now we are going to talk about three general considerations of pipelines, and these are actually what the advantages of pipelines are. So these three considerations are actually what are responsible for offering whatever advantages pipelines actually have. These are the reasons for those advantages, and these are speed up ratio, and throughput. So let's talk about each of these one by one. First, speed up. So speed up is a quantity that serves as an indication of the efficiency of a pipeline. So simply, it measures the efficiency of a pipeline in terms of the number of clock cycles used to complete a certain task. Now, see, efficiency can be measured in many different ways, in many different circumstances. But when we're talking about speed up in context of pipelining, the idea is to measure the number of clock cycles required to complete a certain task so that we can compare how much time is taken to complete that task in a pipeline system versus how much time it took to complete the same task in a non-pipeline system. So that would give you some idea of whether or not pipelining has actually given you some advantage or not, right? Then comes speed up ratio. So speed up and speed up ratio are very closely related to one another. Speed up ratio is a number that measures the relative performance of two systems processing the same problem. So naturally, in the context of pipelining, speed up ratio measures the performance of a pipeline system in contrast to a non-pipelined one. Now again, these concepts will become clearer when we take a look at some numericals. Finally, we have throughput. Now, throughput is something that you generally might have heard in other contexts as well. So it's not a concept that's specifically relevant to only pipelines. So in computer systems, throughput is something that throughput is it's a metric that's measured for many different objectives. In case of pipelining, throughput is the number of instructions executed in the system per second. So very simply, so this is speed up ratio, and throughput is what is how actually we measure the advantage of a pipeline. All right, now we're going to talk about them one by one. So let's first start with speed up. Consider, for instance, that you have a k-segment pipeline with a clock cycle time TP, and we're going to use this k-segment pipeline to execute n tasks. So the number of tasks is n, number of segments in the pipeline is k, and the clock cycle time for each of those tasks is TP. Now, see, so the first task requires K into TP time to complete, right? Because TP is the clock cycle time and K is the number of segments in the pipeline. So each task will have to move through all of the segments of the pipeline. So totally the first task will require this amount of time to complete its operation. Now first task has been executed. Now we're left with n-1 tasks. Now the remaining n-1 tasks will emerge from the pipeline at the rate of one task per clock cycle. So that means they will be completed after time equal to n-1 into TP, right? So the first task takes KTP time. The remaining n-1 tasks will take n-1 TP. Therefore, the completion of a total of n tasks in a K segment pipeline will require KTP plus n-1 into TP time, which is K plus n-1 clock cycles, because TP is simply clock cycles, right? So K for the first task and n-1 for the remaining n-1 tasks. This is the amount of clock cycles, this is the amount of time it will take to complete n tasks in a K segment pipeline. Now if you remember a previous discussion in the previous video, in problem 2 we drew a space-time diagram to count the number of clock cycles it would take to execute 8 tasks in a 6 segment pipeline, and it came out to be 13. And at that point I told you that there are 2 ways of finding out the time it actually takes to complete a certain number of tasks in a certain sized pipeline. One of them is to draw a space-time diagram and another one is the formula, and this is actually that formula. So if you want to go back and take a look at that question again and compute the number of cycles using this formula instead, you would get the same answer, because in that case K was 6 and the number of tasks were 8, right? So putting all that information here, we get 6 plus 8 minus 1, which is 13. Alright, let's take a look at another example. Okay, do you remember this diagram from our first video, the previous video? So we were supposed to execute this specific arithmetic operation for I is equal to 1 to 7. This is the pipeline that we drew for that. This is a 3-segment pipeline. So in this example, the time required to complete all the operations, that is this thing for 7 values of I, is K plus n minus 1, right? So K is the number of segments. In this case, we had 3 segments. N minus 1 in this case is 6. So that gives us 9 clock cycles. And you can actually verify this again. When we were discussing this example in the previous video, we took a look at a table of register content. So we can pause this video, go back to the other one and take a look at it. And we have seen that it took actually 9 clock cycles to do that. So again, you can either use the diagram and draw the space-time diagram, or you can just simply use the formula. Now, what's interesting to note here is that without pipelining, the same operation would have taken 7 times. So 7 into 3, that is 21 clock cycles. 7 tasks and 3 clock cycles for each task. Now this is something you have to understand. Why is it taking 3 clock cycles for each task, right? For one clock cycle, R1 and R2 are being loaded, right? In the next clock cycle, R3 is receiving the result of multiplier, R4 is receiving your third variable, and in the third clock cycle, R5 is receiving the final result after addition. So 3 clock cycles for one task. One task means one value of I, and just multiply that with total number of values of I, that is 21. So you can see 9 versus 21, and this is speed up. So this is nothing but speed up, right? This is a speed up that pipelining provides when compared to non-pipeline systems. So this is simple enough. All right, the next concept is speed up ratio. Again, these two concepts are closely related. That was speed up, this is a ratio. Now the speed up of a pipeline processor over an equivalent non-pipeline processor is defined by this ratio. Now, if we are going to actually talk about the comparison of a pipeline system and a non-pipeline system, then a ratio comes in handy. And a ratio is nothing but you take the total time required by a non-pipeline unit to complete n tasks, and you divide that with the amount of time it takes for a pipeline system to do the same task. So n times Tn is simply the time required by a non-pipeline unit to complete n tasks, right? Tn is the time it takes to complete one task. And k plus n minus 1 you already know from the previous discussion. This is the time it takes to complete n tasks in a k segment pipeline. So you are dividing this non-pipeline time with pipeline time, and that is simply speed up ratio, right? Now see, let's take a look at this equation in a bit more detail. If the number of tasks increase, that is, if n increases, n will eventually become much larger than k minus 1, because a pipeline is never going to be as huge as the number of tasks. If you have 10,000 tasks, suppose, your pipeline will never have even 1,000 segments. That would be too inefficient, right? So k minus 1, this number is always going to be very, very small compared to what n can be. N can be anything. N can approach very large values. K minus 1 will be small because k will be relatively small, right? So when n is too big and k minus 1 is very, very small, almost negligible, this value k plus n minus 1, it will approach the value of n. It will be almost the same as n, all right? When we put this information, k plus n minus 1 approaches n, in this equation, you get this. Just put it in, and you will get speed up as Tn divided by Tp, which is simply, this is the time it takes to complete the task in a non-pipeline system, and Tp is the time it takes to complete the task in a pipeline system. So simply now you're dividing Tn by Tp, and that gives us the speed up. But that is only valid when n is very, very large, very large. Now let's focus on this new equation that we've got. So if we assume that the time it takes to process a task is the same in the pipeline and the non-pipeline system. Now we're saying, if we assume that the time it takes to process a task is the same in a pipeline system and a non-pipeline system, then that means Tn will be KTP. Now you have to be very, very sure of how we're getting these. So if you want to pause, if you want to take a break, the point is, all of these, the results that we're obtaining, it must be clear in your head how we're getting that. See, if we are saying that the time it takes to process a task is the same whether it's a pipeline system or a non-pipeline system, that means Tn, which is the time it takes in a pipeline system, non-pipeline system, will be k times. Why k? Because the pipeline has k segments, right? So every time that task moves through each of the segments, it will take more time and more time and more time. So Tp is the time the task takes for one segment. So KTP will be the time the task takes for all the segments combined, and these two values will be equal because this is what we're assuming. Now if we substitute this thing in this formula, what do we get? S is equal to K. Speed up ratio is simply the number of segments in a pipeline, and this result is something which is very important. The interpretation, the implication of this result, that speed up is the same as the number of segments in a pipeline, it's an important result. Okay? This shows that the maximum theoretical speed up that a pipeline can provide, the maximum value of S that we can hope to achieve in a pipeline, is equal to the number of segments in the pipeline. Equal to the number of segments in a pipeline. Now this result is important, but what's more important to see, is that the word we have chosen to use here is theoretical. Why is it theoretical? It is theoretical because it's important to understand that in order to duplicate this theoretical speedup, if you want to actually make a pipeline where S is equal to K truly, practically, not just theoretically, it is necessary to construct K identical units that will operate in parallel. So it's, if you want S is equal to K, then all your segments in the pipeline have to be exactly identical. Their processing times have to be identical. Their delays have to be identical. Their error rates have to be identical. Their rates of failure have to be identical. If one is working, each other segment is working exactly like it. If one fails, they all fail. And that kind of perfection is impossible to achieve in a realistic setting. And that is why we call it a theoretical speed up. Because it's theoretical, it's hard to achieve in real life because it's impossible to construct K identical units. No matter how hard you try, there will be some minute variation in the segments which will result in some minute variations in their processing times, which means that you can never have S is equal to K. The best you can do is you can have S very close to K, something multiplied by K, but not exactly K. Never, right? That's why the term theoretical is important. It's important to understand. All right, let's move on to our third general consideration and the third source of advantage for a pipeline. That is throughput. Throughput is the number of instructions executed in the system per second. Again, since we're talking about advantages, so it's also important in a way to know how many instructions our system, our pipeline system, can execute in a second. That's also an important measure of its efficiency. Now, the formula for throughput is very simple. See, it's 1 divided by CT, where CT is a cycle time, and cycle time is nothing but the total time it takes to complete a task in a system. 1 divided by the total time it takes to complete a task in a system is the throughput, is the number of instructions executed per second. All right. Now let's take a look at some exercises. We are going to solve some numericals. All of them pertain to speed up ratio, throughput, cycle times, and similar concepts. Problem 1. Determine the number of clock cycles that it takes to process 200 tasks in a 6-segment pipeline. So we're supposed to find out the number of clock cycles it would require to process a total of 200 tasks in a 6-segment pipeline. Now, if you remember the formula, this problem is straightforward. See, number of segments is given in the question, K, 6. Number of tasks, N, also given in the question, 200. The formula for computing the number of clock cycles required was K plus N minus 1. Simply putting all the information available directly from the question into the equation, and we get 205. So we require 205 clock cycles to process these many tasks in this sized pipeline. This was simple enough. Moving on, problem 2. A non-pipeline system takes 50 nanoseconds to process a task. The same task can be processed in a 6-segment pipeline with a clock cycle of 10 ns. Determine the speed-up ratio of the pipeline for 100 tasks. Also, what is the maximum speed-up that can be achieved? All right. See, again, all the necessary information is available in the question. Tn, which is the time it takes to process a task in a non-pipeline system, Tn, that is 50 nanoseconds. The size of the pipeline, the number of segments in the pipeline is given, K is equal to 6. The clock cycle in case of the pipeline system, that is Tp, is given 10 ns. And the number of tasks that we are supposed to execute using this pipeline is 100, right? So we have to find out the speed up ratio and the maximum speed up. So let's first take up the speed up ratio part. Again, this formula, we just discussed this. Speed up ratio is given by the time it would take to execute all of these tasks in a non-pipeline system divided by the time it would take to execute all of these tasks in a pipeline system. You simply divide them This was the formula which we just discussed. Just put everything in there, and this is the speed up ratio we get. Now this is nothing but this symbol represents time, so you must be aware of this, right? So 4.76 times, what this means is the speed up ratio that we obtain if we chose to go with the pipeline system would have been 4.76 times. That is, your pipeline system is 4.76 times faster than your non-pipeline system. That is what this explains. We can then find out the maximum speed up. So maximum speed up, not maximum theoretical speed up, that is s is equal to k, so that should be s is equal to 6. But you know now that theoretical maximum theoretical speed up is not it's not feasible in real life situations. The maximum speed up you can get is Tn divided by Tp. Again, it was discussed previously, and this is simple enough. You get 5. So maximum speed up that you can achieve by using this type of pipeline with this type of clock cycle is 5 times. That is the maximum you can. This is the real value, and this is your maximum value. Okay, so this is how you solve these kinds of problems. Moving on, problem 3. The 5 stages of a processor has the following latencies. So suppose we have a hypothetical processor and it has these 5 stages: fetch, decode, execute, memory, and write back. Now latencies is basically another word for delays, right? Okay, assume that when pipelining is used, each pipeline stage costs 20 ps extra for the registers between pipeline stages. Now you remember, between every segment, for every segment of the pipeline there are registers. Now registers have their own delay, so there's a certain amount of delay that every register has when data goes in and data comes out. So these are the delays of these stages, plus there is some kind of delay for all the registers that are involved in the pipeline. And now you have to answer the following questions based on all of this information. First, what are the cycle time and throughput in case of a non-pipeline processor? If these stages were supposed to be executed in a non-pipelined manner, what would be the cycle time and throughput? And what would be the cycle time and throughput if a pipeline processor was used? So again, the same stages, but now pipelining will be used. So you have to find the cycle time and the throughput in each of these cases. So let's first take up the first part. In case of a non-pipelined processor. Now cycle time, the computation of cycle time in case of a non-pipeline processor is very simple. All you have to do is simply add up all the delays or all the latencies of all the stages of the processor, and you have already been given all the stages of the processor, and each of the latency is also given. So you simply add up 300 ps plus 400 ps plus 350 ps plus 550 plus 100 ps, right? Since there is no pipelining, the cycle time must allow an instruction to go through all stages in one cycle. The instruction will first go from stage 1. It will take the instruction 300 ps to be executed. Then the instruction will move on to the next stage. This stage will add in an additional delay of 400 ps. Then the instruction will move on to the third segment, where it will take 350 ps to execute, and so on and so on. And by the time it passes through all the stages, it would have taken this much time, that is 1700 ps. Simple enough. We have simply added the latencies or the delays of all the individual stages involved. And throughput, as you already know how to compute throughput, that is 1 divided by cycle time, and you already have cycle time. So throughput comes out to be 1 divided by 1700 instructions per second. That is your throughput. Now we can do the same thing to find out the cycle time and throughput in case of a pipeline processor, but with a very significant, albeit minor, modification. See, in case of a pipelined processor, cycle time is computed in a different method. So what we do is, because we are going to execute all of these stages in parallel, it's no longer sequential because pipelining is supposed to be used. That means when one instruction is being decoded, another one is being fetched. or when one instruction is being written back, another one is being executed, another one is being decoded, another one is doing some kind of memory operation. That is the whole idea behind simultaneous operation, right? So we're not waiting for each instruction to pass through this stage and this stage and this and this and this, and then we are bringing the next instruction which will also pass through these stages sequentially, and then we are waiting for that instruction to finish so we can bring the third. No, that's not what we do in pipelining. In pipelining, we do all of this simultaneously, which means that the largest amount of time any instruction will take will be dependent on the largest latency of any of the stages. Because think about this. In this case, this is the largest latency, right? 550 ps. All the other 4 stages take time less than this, which means when an instruction is in stage 4, right? Say we have an instruction which is currently being executed in stage 4 of the pipeline. This stage is taking 550 ps. So by the time this instruction finishes its operation, all the other instructions which were being executed in all the other stages would have already finished their execution, right? Because all of these times, all of these latencies are smaller than 550. So if instruction X, suppose, is being executed in stage 4, then all the instructions A, B, C, D, E, F, in whatever stage they are being executed, they will definitely finish their execution before instruction X does, because all the stages take less time than stage 4. So that means when pipelining is involved, if you have to compute cycle time, your cycle time will depend on the largest delay or the largest latency of all the stages given to you, and this is the largest one, so 550. Also, in pipelining, another thing that comes into the picture is this time, is the time it takes for the registers to start reacting. That is the latency of the registers, right? This latency is considered only when we're talking about pipeline system. It doesn't matter when we're talking about a non-pipeline system, because the register plays no part when system is non-pipelined. Why would you need a register if you are already waiting for each instruction to pass through each of these stages individually? You give the input and then you get the output. There's no register involved. Registers are only needed when you temporarily need to store the data, and that happens when multiple instructions are being executed at the same time. To store the multiple data, you need the register, and when you need the register, then you have to count its delay as well, and which is what we have done, right? So this was a very long description for something that's not that complicated, but I need you to understand this very, very clearly. When we're talking about the cycle time of a non-pipeline system, you have to add all of these up. But when we're talking about in pipelined system, you only have to consider the largest latency and whatever the latency of any of the registers is. So this is the value you get. 570 ps is your cycle time in a pipelined processor. And again, throughput, you know how to compute. 1 divided by CT, 1 divided by 570. Instructions per second is your throughput. All right, let's move on. Problem 4 now. Consider a pipeline having 4 phases with durations 60, 50, 90, and 80 nanoseconds. Again, you see the terminology varies. 4 phases or 4 stages, it's all the same thing. Duration, latencies, delays, whatever, it's the same thing. All right. Given latch delay, that is delay due to each register, again a new terminology. So usually we call them register delays, but now you know another name for it, latch delay, right? So the register delay is given to be 10 nanoseconds, and you're supposed to calculate the following. First, pipeline cycle time, non-pipeline cycle time, aka non-pipeline execution time, speed up ratio, pipeline time for 1000 tasks, sequential time for 1000 tasks, sequential is nothing but non-pipelined, and throughput for pipelined execution. Let's take a look at them one by one. Pipeline cycle time, you know this already, so you have to add the maximum delay of any of these stages, which is 90. with any delay of the registers. So 90 plus 10, this is your cycle time in case of pipelining. Cycle time in case of non-pipelining, otherwise known as execution time, simply add 60 plus 50 plus 90 plus 80, which gives you 280. We did this previously, right, in the previous problem. Speed up ratio. You know how to compute speed up ratio. Divide the execution time of the non-pipeline system with that of the pipeline system, and both of these you have computed in the previous parts. Simply divide them. So the speed up is 2.8 times. 2.8 times, right? Pipeline time for 1000 tasks. Interesting. Pipeline time for 1000 tasks, and this is something you know already. Pipeline time for 1000 tasks is time taken for the first task plus time taken for the remaining 999 tasks. We have had this discussion previously, so just take a break and quickly go back, and this will be clear to you. So pipeline time for 1000 tasks is actually the time taken for the first task plus the time taken by the remaining 999 tasks, which is 1 into TP, right? 1 into 4 clock cycles, because there are 4 phases. So the first task, only one task is there, so 1 into whatever the clock cycle time is, which is 1 into, because there are 4 phases, and 999, the remaining 999 will come out of the pipeline 1 per clock cycle, 1 plus per clock cycle. So 4 into cycle time plus 999 into cycle time, 4 into 100 nanoseconds. This is just what we computed in the first part of this problem. 999 into 100 nanoseconds. Add them up, and this is the final value you get. So this is the pipeline time for 1000 tasks. Then you can find out the non-pipeline time for 1000 tasks. This is simpler, right? 1000 into, just multiply the time taken for one task with 1000, because this is a sequential system, this is a non-pipeline system. So whatever time one task takes, just multiply that with the number of tasks you have in your system, and that will give you, because all of those tasks are going to be executed in sequence. First one is executed, then the second one is executed, then the third one. So whatever time one task takes, multiply that with the number of tasks, and you have time for the 1000 tasks. All right, throughput again, number of instructions executed per unit time, number of instructions executed per second. We have 1000 tasks, and this was the number of time it took to execute those tasks. So throughput will be 1000 divided by this value which we just computed. Now here's an MCQ for you. A 4-stage pipeline has the stage delay as 150, 120, 160 and 140 nanoseconds respectively. Registers are used between the stages, and they have a delay of 5 nanoseconds each. Assuming constant clocking rate, the total time taken to process 1000 data items on the pipeline will be, and you have these 4 options. Now if you take a look at the question again, it's a 4-stage pipeline, right? These are the delays of all those 4 stages plus the delay of the register, and you are asked to find the total time it would take to process 1000 data items. Now this question is up to you, and all the information you need on how to solve this can be obtained from the previous question, the one we just solved, right? So the answer for this is this one, and you can compute it and cross-check it, and if you need to know how it was done, the complete solution can be found at the end of this video. But again, all the ammunition you need to solve this was just discussed in the previous question. Alright, another MCQ for you. Consider the following instruction pipeline. So we have, okay, now we are going to talk about instruction pipelines in detail in the next video. But here you just have to understand that this is a pipeline like any other pipeline, right? We have 1, 2, 3, 4 stages, and we have registers between each of these stages. So the stages have their delays. It's written here 5, 6, 11 and 8, and all of these intermediary registers also have their delays. 1 nanosecond each, right? So just focus on whatever information is given. The concept of instruction pipelines will be discussed later on. Now, given this setup, what is the approximate speed up of the pipeline in steady state under ideal conditions when compared to the corresponding non-pipelined implementation? So long story short, what you have to find out is the speed up. And again, you're familiar with all the formulas for the speed up. Number of stages is given, all right. Delays of each of these stages plus the delay of the registers is given. So when you solve it, you'll find the answer to be this value. This is the approximate speed up, 2.5 times. Again, all the information you need on how to solve this has already been discussed. Complete solution can be found at the end of this video. This is it for this video. These are the solutions to the MCQs that we just saw. You can take a look at them at your own discretion. All right, so a quick recap. So far in this video, we have discussed the general considerations of pipelines and how these considerations, namely speed up ratio, and throughput, lead to the advantages that we observe from pipelines. Plus, we solved some numericals related to these three concepts: speed up ratio, and throughput. In the next video, we are going to be talking about the different types of pipelines, namely arithmetic pipelines and instruction pipelines, and then again we'll take a look at some relevant exercises.